Alright, hello everybody, welcome to a very quick video on linear regression. This comes from Chapter 7 in Fields, Discovering Statistics with R. And here we go. So as my notes tell you there, the general form of a linear regression as a model is the linear model, which is LM, of an outcome, which is a number, by number and rank and binary. So the outcome is going to be some interval or ratio value. So there are a few assumptions here, but unlike other scenarios, we actually test the assumptions last because we have to build the model before we test and see. So the first thing I'm going to do is create a data set like I have so many other times before. You'd think I could have loaded for you already, but whatever. Take a deep breath. So the data I'm loading right now is album sales 2. Running a quick summary on the data. There's our data. The number that we're trying to predict is sales. So we're going to run straight in and create 4 models. We could create more than this. And there are reasons why you may choose to do different things than this, but that's what I did here, not a problem. So as a rule though, you're going to start with the thing that you think is most obvious to matter. You can run correlations ahead of time to identify that. Then systematically add the other 2, and then the other 3. So the only thing that isn't here is the interaction between airplay and attract, ignoring adverts. So if we wanted to, we could add that in there just for fun. I will, but it'll confuse us a little bit with which number it is. And like I said, we started with adverts, so really we probably want to keep adverts around the whole time. But since somebody asked last time, I will recreate that. So I'm just going to clear the screen. Here are our new models. And what I did was add the interaction between attract and airplay and the pair of 2. So we really have most every interaction we can have here, I think. Yeah. Great. So with that said, we can run a ANOVA in order to see if there is reason to believe that one of these is different from the other. So, oops, should be a lowercase m. And we have reason to believe that 5 is significantly different and 2 is significantly different. The other one's not so much. Alright. So 5 is the one that has all 3 of those. So we could say 5 and compare it to, say, the next closest, which will get rid of 2. Check that. Okay, and again, their third variable is different than either of those. So that's our p-value right there. Great. And again, I can break this down any more than I want to. It doesn't really matter. The point is that 5 is going to consistently be better than either of those. Alright, so now that I've got that, I have a model. Let's look at our model. So we can do a summary .lm of our model. And this gives us a whole pile of information. So first thing we look at is the p-value for the model significant? It is. Excellent. Now, the p-value is significant. We want to check and make sure if one of the variables we used in our model was significant. They all are. Last up, we want to look at the r-squared, somewhere between 66 and 66%. So yeah, call it about 66% of the variance in this model can be explained, or so the variance in sales can be explained by our model, which includes adverts, attraction, and airplay. This estimate value tells you how many more sales are getting for 1 unit of each of these things. So if you know the price of each of those things, you can make an informed decision about whether or not you should buy more advertisements or not, more airplay or not, etc., if those are things that you can buy. Now that we've done that, let's go check some of our assumptions. So I need car, which we do all the time. And from car, I'm going to use the Durbin-Watson test, this test for the independence of errors. And I'm going to do it on my model 5 because that's the model we ended up with. I do not have a significant p-value, so that is not violated. Next off, I'm going to test for multicollinearity. If these numbers are above 10, I'm concerned. They're not above 10, I am not concerned. Next, I'm going to check my plot. This is for a normal distribution of stuff. I want to see an approximately horizontal line, which I do. I want to see pretty much a diagonal line, which I do. I want to see these pretty evenly spread throughout, which I do. And though this is a funnel shape, what we're really looking for is to make sure there aren't clumps somewhere in here. This is kind of the least useful of those graphs, in my humble opinion. Alright, so now that we've done that, our last step is to make sure that our residuals are all nice and even with each other and give us a bell curve. So I just called that. In order to view it, I need to go to Window and View. And that's a nice, normal looking distribution, so I'm feeling pretty good. We want it to be around 0. It appears to be around 0. It goes down on the sides. It's pretty much what a bell curve should look like. None of those violate our assumptions. We're pretty much good to go. That's it. Hope you enjoyed.